Welcome back, everybody. Today we're going to be talking about vectors. And this is just a start on vectors. This is not by all means everything you need on vectors. This is going to be a start. The reason we're starting from scratch is because a lot of students don't have a great deal of background with vectors. So I like to start from the most basic and work my way up. That way we're all on the same page. All right, so let's start with what is a vector. All right, there's a lot of quantities like temperature, mass, volume, all right, that use a single number to characterize that particular thing. And then there's an appropriate units of measure. So for example, with temperature, right, you can have 59 degrees centigrade, you could have 91 degrees Fahrenheit. It's a single number, and we have appropriate units. These types of numbers are called scalar quantities, and things like mass or volume are all scalar quantities, right? One number, one set of units, and you have your thing. Now, not everything is a scalar quantity. For example, things like force, velocity, acceleration, can't be characterized by a single number with units, all right? They not only have a length, but they also have a direction, all right? And when you can't characterize it with a single number, we call it a vector quantity. All right? And a vector is denoted with not just a length, but a direction. So, for example, if I have point P here and point Q here, we can call this vector PQ, right? Or if I call it, right, if I say this is vector V, I could say vector V, right? And if you wanted to put units in here, or you wanted to put numbers in so you can know where it is in space, usually you use those pointy brackets, all right? So also, if we want to know the length of PQ, that's called the magnitudes, all right? So the magnitude is denoted by two straight double lines. So if I want to know the magnitude of PQ, I would write it like that. And that would give me magnitude, excuse me. All right. So, other things that we can do. Right? I'm just going to shrink that up a little bit, because what I'll tell you is that if we have two vectors that are equivalent, all right, write this down, they'll have the same magnitude and the same direction. All right, so off of that, let's go to the first example. Let V be the directed line segment, PQ, from 0, 0 to 3, 2. Let U be the directed line segment from 1, 2 to 4, 4. Show that U and V are equivalent. All right, so the first thing we need is the magnitude of PQ and of RS. Now, length can be denoted by the distance formula. So if I'm trying to apply the distance formula here, right, I have a square root, and I'm going to take the final minus initial, right? So the final point, right, the final x-coordinate is 3 minus our initial x-coordinate 0. I'm going to square it, and I'm going to add it to the final y-coordinate, which is 2. The initial y-coordinate, which is 0, and I'm going to square it. This is very similar. This is the exact same thing as the distance formula you've learned before. The reason it's the exact same thing is that this particular vector is in two-dimensional space. So it is basically the equivalent of an xy point to an xy point, right? That's why it's a directed line segment, all right? So I'm going to set up the second magnitude. So we have our final y coordinate is, or x coordinate is 4, minus our initial x coordinate 1 squared, and I'm going to add that to 4 minus 2 squared. All right, so at this point, I'm going to ask you to pause the video and work on the magnitudes, and I'll give you the answers on the back end. All right, so you should have done the algebra. Shouldn't have been too hard if you're looking at analysis concepts. And this should have been the square root of 13 and the square root of 13. Now, we have just proven that the two magnitudes are equal. Now we have to show that their directions are equal. In two-dimensional space, we can show direction by using slope. So again, our slope formula is going to be y2 minus y1 over x2 minus x1. So I need to show the slope of PQ, and I need the slope of RS. All right, so at this point, once again, I'm going to ask you to stop the video. I'm going to just inch that up a little bit, get a little more space. And I'm going to ask you to do the slopes of both line segments. All right, you should have been able to plug in your points appropriately. I got a slope of 2/3 and a slope of 2/3, which shows me that they're going in the exact same direction. Remember, slope is rise over run, so they're both rising 2, and they're both running 3 to the right. All right, so if they show the same magnitude and direction, the two vectors are indeed equivalent. Now, a fun fact that I want to talk to you about is this. So I'm going to shrink that up a little bit. If I have a vector v, I'm going to erase this. I'm just going to put my vector v here. All right. If I want to change just vectors v direction, I'm going to multiply times -1. So if I have vector v and I'm going the opposite direction, it's the negative of vector v. Again, not a revolutionary concept, but could help you solve a different problem. Now, you won't always have the starting and ending point of each directed line segment. All right, so we need to know how to take our line segment and turn it into a vector. So for example, if your initial point, I'll make that a little bit bigger for you. If your initial point is 3, -7, and your terminal point is -2, 5, I just want to find vector PQ. All right. Now again, I'm not always going to have the starting and ending points, so I need to have a way to represent my vector if I didn't have the starting and ending points. So it could start and end any place, but it would still have the same length and direction. All right. So basically, what you do is you do final minus initial. So vector PQ, right, is going to be, let's represent it as v1 comma v2, right? And v1 is going to equal final minus initial for my x coordinates. So my final is -2, my initial is 3, so I'm going to subtract 3, and I get -5. And for v2, again, final minus initial in the y direction. So I have 5 minus -7, which equals 12. So vector PQ is going to be -5, 12. And you could say that that's how you represent the vector. And this is more commonly the way you'll see vectors represented. Now, let's say I wanted the magnitude of this vector. You can do the magnitude the exact same way we did in problem 1. However, we've already done final minus initial, so we don't necessarily have to do that again. What we can do to get the magnitude of PQ is just, right, we take the square root of each individual element squared. So I have -5 squared plus 12 squared. I've seen other professors kind of tell you magnitude as you square them, you square each element, add them, square root them, so it's kind of a nice way to remember it. So at this point, I'm going to ask you to pause the video, quickly go through the calculation, and we'll talk about the answer on the back end. All right, so -5 squared is 25, 12 squared is 144, so I have the square root of 169, and you should know that one as 13. Magnitude won't always come out as a whole number. More than likely it'll come out with some sort of square root in it, but every once in a while you get lucky. All right, now before we end, we're going to do a little bit with vector operations. All right, now some of the operations are very similar to scalar operations. So for example, if you wanted to add vectors, you can just add each element together. So you add the first element with the first element, second with the second, third with the third, if there's 3, if it's in 3 space. Or if you were going to multiply a vector times a scalar, right, you could multiply each element times that scalar. So let's just jump right into an example here. So I have vector W, and I'm multiplying it times the scalar of 1/2. So I have 1/2 times 3, 4, right? And remember what we said was that if we are going to multiply our vector times that scalar, which of 1/2, we take the 1/2, multiply it times 3, so that's 3/2, and multiply 1/2 times 4, and I get 2. So there is your final answer. If I'm going to subtract 2 vectors, right, I'm going to subtract the first elements. So I have -2 minus 3, and then subtract the second elements of 4 minus, or excuse me, 2 minus 3, and then U minus V is, or W, okay, so that's 4 minus 5, excuse me, because we've got to do W first, 4 minus 5. And when we do this, I get -2 minus 3 is -5, 4 minus 5 is -1, and there is your answer. All right, now I'm going to try to combine the two. So I'm going to take W and I'm multiplying it times 2. All right, so if I look at W, I can multiply it times 2 right away. And I'm going to rewrite the problem, excuse me, using my vectors. So I have -2, 5, and I'm adding that to, and instead of writing 2 times 3, 4, I'm going to write just 6, 8. So now I'm going to add the elements together. So I have -2 plus 6, and I'm going to have 5 plus 8. So -2 plus 6 is 4, and 5 plus 8 is 13, and there is my vector. And again, if we have a vector in 3-dimensional space, right, you would add the first elements with the first elements, the second elements with the second elements, the third elements with the third elements. It would just extend from there. All right, so Now we're going to talk about a unit vector. I'm going to come back up here. And I'm going to shrink it down a little bit so I get a little space. If we were to talk about something like a unit price, like for example, if I have 10 apples and it costs me $4, right? If I wanted the unit price per apple, that would be, what is the price of a single apple? Well, you would do $4, divide it by 10, and you would get 40 cents. And it's the same idea of what we're going to do with vectors, all right? So for example, if we have what we call a unit vector, all right, basically what we're taking the vector and we're making it a unit length of 1. So our unit vector formula is basically going to say, I'm going to call my unit vector u, is going to be, let's say our vector is called v, and we're going to divide by the magnitude. We're going to divide by the length, and that basically will give me an equivalent vector. It'll just have a length of 1. All right, so let's scroll back down. Let's see if we can. All right, so here we go. So I have a vector already, -2, 5, and I want to find the unit vector. All right, and then I want to verify that that particular unit vector has a length of 1. All right, so what we're going to do is this. We're going to start with our formula, which is vector v divided by the magnitude of vector v. But we know what vector v is, we just don't know what our magnitude is. So let's start there. So I have this square root, right? I'm going to square them, add them, square root them. Thank you to whoever told me that. That is a very nice way to remember it. All right, so if I have -2 squared, that's 4. 5 squared is 25. So my magnitude is the square root of 29. Now, in order to write it in this fashion, I could write it a couple of different ways. I can write -2 divided by the square root of 29, comma, 5 over the square root of 29. And there is my unit vector. There is another way you can write it. All right, so the other way you can write it is, you could write it as, let's say, 1 over the square root of 29 times -2, 5. Excuse me, I'm going to write with my pointy brackets. You can see that they're equivalent. I kind of like writing it like this. All right, so now we need to verify that the magnitude of our unit vector is indeed 1, which basically means that I need the magnitude of u. All right, so I'm going to scroll that up, get rid of my extra markings. All right, so I'm going to square them, add them, square root them, right? My elements of u. So I have 5 over the square root of 29 squared. All right, so if I square the elements under the square root, -2 squared is 4 over 29 plus 25 over 29. And then what we can see clearly is that 4 over 29 plus 5 over 29 gives me the square root of 29 over 29. And if I simplify that first, I have the square root of 1, which equals 1. Hence, I have verified that the length is 1. All right, so now in general, I've written my vectors kind of looking like ordered pairs. They're not really, but kind of looking like ordered pairs. Mathematician named Hamilton, who was Irish, came up with notation to show direction. So, for example, I, J, and K. So the I would be, let's say, the X direction on our coordinate plane. J would be, in a sense, the Y direction, and K would be the Z direction if we had a three-dimensional coordinate plane. So if I had an initial point of, let's say my initial point was P of 2, -5. My final point was Q of -1, 3. All right. I want to find vector. I want to find the, and I'm going to let vector V equal 2I minus J. All right. And then put little hats on them to show that it's a vector. All right, so the first thing I want to do is I want to find the vector for my directed line segment. So how do I do that again? I'm going to call that vector, all right, lack of originality. I'm going to call it U. So I'm going to say U equals, right, and I have my final minus initial, so -1 minus 2. And I'm going to have 3 minus -5. So my vector U is going to be -1 minus 2 is -3. And 3 minus -5, +8. There is my vector. You could write it this way, or you could write U equals -3I plus 8J. And this is called the linear combination. So you could write the vector either way. All right, so let's say I wanted to take it to that next level, and I want to find, all right, now that I have U and V, find 2U minus 3V. All right, well, U is -3I plus 8J, so I have 2 times 8J. And I'm going to subtract that from 3V, and V was 2I minus J. And I knew that because that was in my problem, right? I stated that as a given. All right, so now we're going to use our scalar operations. We're going to distribute. So I have -6I plus 16J. I'm going to distribute my -3, so I have -6I plus 3J. And now I can combine my like terms. All right, so I have -6I minus 6 more I gives me -12I. And I have 16J plus 3J plus 19J. And there is my vector. All right. So that is just a quick hit, a quick start on vectors. Hope you enjoyed it, and I will see you next time. Thank you.